Physics is not physics. It's not okay. Yes. Yes, sir. Welcome everyone. I'm very happy to have Anirban here from IIT Gandhinagar. Anirban has actually visited us before 10 years ago. But when I asked about that this morning, he said he's forgotten all about that. And the reason is that when he visited us, he did not know enough about coresets. So today he's going to tell us about coresets and maybe he'll remember us.
No. I did remember parts and bits and pieces of it. Nice parts, which was most of it. But yeah, sorry, I should have really said more carefully. Okay, so thanks for inviting me. It's really a pleasure to come and talk in front of this audience. So today I'll talk a little bit about coresets, right? And what I have done, I don't know if it's for the good or bad, is that I've not really focused on one particular result, right? I've taken sort of a slightly high level view and try to tell you what coresets are, what are some important research problems, and what are some results that we have over time. What are some things that we have developed? Hopefully, this will inspire some of you to look at interesting problems related to this, or even apply some of these to the problems that you have. Okay, so this is a picture of our campus. This is one part of the campus that we call the Sandhya Chaya. And the grids there on top, the squares on top are supposed to be reflective of the fashion of flying kites in Gujarat, right? Supposed to be a sort of kites that are up there. So you should really come and visit. It's really a beautiful campus. So we start off with the computational burden of training models. So some of you might already have seen this, but just to remind the others that while we are enthralled by this ChatGPT, the Claude, and many such things, we are also paying a heavy price for it, right? And we don't really realize that always. But if you look at the amount of time it takes to train, the amount of resources it takes to train one of these models, it's really, really huge, right? Just as a comparison, the average American life, right? Not an Indian life. The average American life 1 year is like 32,000 pounds of carbon dioxide. The average car in its entire lifetime runs about 126,000 pounds of carbon dioxide. Training one of these NLP transformers, one of these bigger transformers, along with the architecture, search and everything, takes around 626,000 pounds of carbon dioxide. So about 5 cars, right? So that's huge. Right? And somewhere we have to be careful about this price that we are paying. That why are we doing this? Is it possible to do it cheaply? And I'm not going to go into why are we doing this. That's a more philosophical question. It's an important question, but I'm not going to go into that. What I'm going to talk about is whether it's possible to do it more cheaply, right? Whether we can try to do it more cheaply. So the other way of looking at it is that the data is growing bigger and bigger, right? It's very fashionable to talk about big data, right? And there are many different strategies for dealing with big data. So some of the strategies deal with parallelizing your computation, right? Or even distributing your computation on different machines, like this Hadoop and MapReduce and others. And other things, right? Or the problem is that, or transferring it to GPU, right? The problem is that each of these techniques comes with its own bottlenecks, right? For instance, whenever you go from a single machine, a single thread to a multi-threaded GPU, it comes with its own bottlenecks of the shared memory and having to update the shared memory. You have to tweak your algorithms in order to handle that, etc., etc. When you go from a single machine to Hadoop, for instance, to MapReduce, right? Your bottleneck is not just at that point is not a single machine's power, of course, but it's the network bandwidth, right? Connecting all computers to one another and how the data is transferred from one computer to another. So basically, nothing comes for free, right? Each of these innovations that we bring in to handle big data comes with its own set of resource bottlenecks and requires that either we tweak existing algorithms or we come up with new algorithms that can exploit that platform. The question is that can we somehow have cheaper methods of scaling existing algorithms to our large data sets? And we are, of course, as I always tell my students, that we computer scientists are a bunch of lazy bums. We always try to do things cheaply. Okay, can we do it? Right? So here's one thought, that perhaps all data is not really useful, right? That what if we could reduce the data and then use the existing algorithms, right? We could reduce the size of the data dramatically and use the existing algorithms and still get a similar performance. So how do we formalize this idea? Right? Here is the very high level view of it. That suppose A is an algorithm and D is a data set. Right, and we want to find a smaller data set C, right? And often C will be a subset of D, not always. I'll show you examples when it's not a subset of D really, but it's a representative data set. See, that C will be created out of D, such that A of C is more or less similar to A of D, right? And this we will make rigorous. Right, and the important point will be that the cardinality of C is much less than the cardinality of D. Right, so therefore running the algorithm A on C will be much cheaper. Right, can we do this? Right, is it even possible? So here are some. Here is a very high level roadmap of the talk, and here are some things that people have done. Right, people have applied things like geometric decomposition, and people have applied things like importance sampling. We'll focus more on we focus more on the importance sampling direction. That's the latest and greatest in this line, and throughout when we talk about this, we'll keep two running examples in mind. One example is that of clustering, and just simple k-means clustering. Another example is that of solving a regression problem. Right, we'll keep these two examples in mind, and we'll also maybe talk about, depending on the time, coresets or other problems. Then we'll talk about some extensions of it. Right? Okay.
Yeah, I have a question.
Yeah.
So people often talk about coresets in the context of maximum matching or other problems on graphs.
Right.
Are they similar to this, or are they exactly the same?
Coresets in the context of maximum matching.
Yes, it's something like that. Yeah.
So in maximum matching, I don't know how you would use coresets really. Because in maximum matching you do need access to the entire graph, because technically maximum matching could involve the entire graph.
Yeah, they want an approximation.
You want an approximation of that size. Yeah, so then it would be similar. Okay. We'll then talk about some other applications, and it's model compression, privacy and security, etc.
So is I presume it will show up at some point. So there is also the effort that it takes to construct the coreset. Okay. So
it will show up.
okay.
Okay. And that's an important problem, and that's an important question, because you always want the effort that is taken to construct the coreset to be of much lower magnitude than the effort taken to solve the problem, because otherwise creating the coreset is useless, and we'll quantify it. Okay, so why is this useful? Let's just look at a very toy problem. Right? A very toy problem first, just to see, just to kind of illustrate what you just asked, and just to see whether we can do it. That suppose we have an overconstrained system, so Ax equal to B, but we are told that it is satisfiable. An overconstrained but satisfiable system, Ax equal to B. That's the matrix A, that's X, and that's B. Of course, that's understandable. And The question is the following. So A is of size n cross D. So it's in because it's an overconstrained system, and n is, let's say, much larger than. The question is that do you need what is the solution, and do you need to keep all the rows of A in order to solve this problem? Okay. An overconstrained but consistent linear equation, right? And we know that the closed form for this is that it's x equal to A transpose A inverse A transpose B. Okay. Now, if you think a little bit about what is happening underneath, you will realize that you don't really need that while we are calculating A transpose A, you don't really need all the rows of A in order to get the solution for this. A transpose A inverse A transpose B. Because effectively what is happening is a projection of B onto the column subspace or onto the corresponding row subspace of A, right? And so effectively it is enough if we keep only the D linearly independent rows of A, right? That is enough, right? You would get exactly the same X. Right? If instead of A, you reduce A to keep only the D linearly independent rows of A, that is enough. But coming back to that question in this context, that is this a useful, can we call this a coreset? Is this a useful data reduction strategy, broadly? It answers that it's not. Right? And the very, very simple reason is the following, that if you just calculate the number of operations it's taking to calculate this, it's something like nd squared. It's something like nd squared. Okay, because calculating A transpose A takes times nd squared and then plus other orders of D. nd square plus d cube, I think, or something like that. Now finding out the linearly independent rows of A by using Gaussian elimination or anything of that sort also takes time nd square, right? So then the problem is that what is the point of doing this? Right, then why are we trying to reduce A when reducing A effectively would take the same time as solving the problem?
But I need to know just one instance or repeatedly.
I'm just talking about one instance. One instance. Okay. Then why do we do this? Now, to see why that is important, and I won't go into the details of why that is important because that would be another talk by itself of how to do this, because that would be another talk by itself. But essentially, let's even try to generalize it. Right, and let's even see if it's possible to generalize this. That suppose now we go from the over-constrained and satisfiable to only over-constrained. That I'm not even guaranteeing that it's satisfiable. Right. So now we have Ax close to B. Right, and we're trying to solve. And we're trying to find the x that minimizes Ax minus B according to some norm. The L2 norm is the most obvious norm, but it also could be some other LP norm, right? And this now forms a system of regression problems, right? I'm calling it a system because depending on the norm that you put in, it would be a regression problem in that norm, right? L1, L2, LP regression problem. Right? The question, but I can now go back and ask the same question now. That can I find a coreset that is a subset of rows that gives a close enough solution to this, right? And is that possible now? And now that question is no longer that obvious. That finding out linearly independent rows would give me the correct solution, right? Because I no longer have a closed form. Right? If I have L1 regression, for instance, I no longer have a closed form for that. So I cannot argue that finding out linearly independent rows would be enough. Right? Also notice now that the computational problem of solving this bigger system has blown up. Right? Because either you have to solve a linear program in case of L1 regression, or for LP regression for p greater than 2, you have to solve a convex problem. Right? So it is no longer nd square.
But L2 the same solution would work. For
L2 the same solution would work.
For other.
For other p the same solution would not work. For L1 as well as for L2 the same solution would work. So the bigger question remains that can we find this efficiently, right? Even for L2, that can we find this efficiently? It turns out that there's a long story behind this, and that yes, you can do this. I mean, I hint towards the L2 solution now, but I'll not focus on the L2 solution. We'll talk a little bit about the LP case, right? About the for the LP regression. Right? It turns out that you can define a set of. I'll just talk a little bit about the L2 right now. That given this matrix, you can define a set of probabilities on the for each of the rows, right? And these probabilities are based on the singular vectors. Are based on the left singular vectors of the particular matrix A. Right, it's dependent on the norms of the left singular vector, on the norms of the rows of the left singular vector matrix, and based on if you sample according to those probabilities, right, you do get a set of rows that is that and such that it's enough to solve the problem on the resulting smaller subset. Right. So essentially, the strategy that I'm giving to you again, it's questionable. The strategy that I'm giving to you is that find out the left singular vectors of A, right? Take the norms of the rows of the left singular vectors, define a probability distribution based on these norms because these are now real numbers. Define a probability distribution based on these norms. Sample the rows according to that probability distribution. Right? Then sample only, let's say like D rows according to that probability distribution. Notice N is the number of rows, N is much larger than D. D is the number of columns. So sample only D rows according to that probability distribution. Solve the problem with the D rows. Right? So now it's a D cross D matrix, so much simpler to solve. Solve the problem with the D rows and you will be happy. I promise you that you will be happy. The question then again, what you should ask, as that astute question was made before, is that, but note the first just halt here. Because first you're finding out the left singular vectors. Right? How much does it take to find out the left singular vectors? It takes them ND square. Right? Because that involves the same kind of computation. So even that is not very effective. It turns out. Yeah.
That will just take a random sum of the rows, D many independent random sums already.
D many independent random sums, yes, you could, right? But calculating D many independent random sums would take ND square time.
Yeah, but not ND square was the goal, right? Because the other way is much more expensive.
No, just solving the problem is also taking ND square time. So
even for P more than.
Oh no, not for P more than 2. Not for P more than 2. For P more than 2, so for P more than 2, just calculating random sums of the rows wouldn't work. I'll show you something that works. But calculating random sums of just random combinations of the rows actually does not work. Right? You have to select rows for P more than 2. And yeah, unfortunately, I left out the deterministic results here today, but we'll see. Okay. So now the question was that where we are stuck is that I gave you a sort of prescription using the left singular vector, but finding out the left singular vectors also is expensive. So now comes the algorithmic tricks. It is what we really needed are the row norms of the left singular vectors, and it turns out that it's possible to estimate the row norms of the left singular vector without calculating the complete left singular vectors themselves. It's possible to estimate the row norms using different randomized techniques, right? And that involves some jugglery. So we do that jugglery. We estimate the row norms of the left singular vectors, and then we sample using that. And this works for the L2 regression. What happens for LP? What happens for L1? And we don't know yet. I mean, we know at this point, but we don't know. Okay. Here's my next running example of clustering. A very simple algorithm. A question. Well, not so simple. So suppose we are given k points as on the left, and we have been asked to partition it into 3 clusters. Let's say k clusters, whatever. And A of D is the cost of clustering D, the data set with k centers. Right? with k, where here I have just mentioned that k equal to 3. Now the question is the following, that rather than having these so many points, can I somehow have a meta set of points, or meta points, such that the weighted points, right? I'll have xi wi, where wi is the weight of the point xi, and just say that that look, right? Whatever we are clustering on the your best clustering on the case on these point with case centers, I don't know that, but I guarantee you that that give me any case centers. Right? In fact, this is what I'll guarantee, that give me any case centers, cost of clustering this set using that case centers will be very close to cost of clustering that set with the same case centers. Just notice. What we are saying is much stronger. We are saying that give me any case centers, the cost of clustering my points, my new points with those case centers will be the same as cost of clustering your original set of points with those case centers. See, if we guarantee this, then it's enough to take my set of centers, my set of points, a new set of points, and cluster them optimally. Right? We'll show that mathematically right now, because but intuitively, because for any set of centers, my set of points represents your set of points in terms of the cost. Therefore, it's enough to cluster my set of points optimally and take that clustering and sort of show it as a clustering for your set, for the original set of points.
The error here is additive and not multiplicative.
No, the error is multiplicative.
Multiplicative.
The error is multiplicative. You just go there. Okay, so to kind of formalize this, asking me for coffee or which I'm not going to. Okay, so to kind of state the same result for a bunch of different problems. Here is the language that we use. We call it in the query and cost language. Right? What is a query and what is a cost? So a cost is the normal cost. Cost is, for instance, for a clustering, the cost is the cost of clustering these points. Right? For regression, the cost is the final regression value. Right? That is the cost. The total cost of these of fitting this line to this set of points. Okay, that's the regression cost. Okay, and what we say is that let us break down this cost into the points. We say that for clustering, we'll say that the cost is the sum of pointwise costs. Right? For regression, the total cost is the sum of pointwise costs. Okay? And then we say that my query is a proposed solution. Right, and these are, for whatever reason, these are termed queries in literature. But for regression, my query is a vector, right? A d-dimensional vector. It's n cross d. My query is a d-dimensional vector. I fit that vector. I evaluate the cost of that vector. Right? And for clustering, my query are case centers. I give you my case centers and I tell you find out the cost of these case centers. So that's my query. Okay, so now as I mentioned, that the total cost f of q, what we write as f of q, can often be represented as an aggregation in all these problems, right? In the least square regression, the total cost is the sum over all rows ai. So imagine ai is the row of the matrix A, ai transpose q minus bi whole square, right? Q is the potential solution vector. Right, minus bi is one entry of this matrix B. So ai transpose q minus bi square. I don't need this. These are all scalars. Okay. For k-means clustering, the cost is the cost of every point, the distance of every point to the set of centers, and then you square the distance. For k center, the cost is you take the distance of every point to the set of centers. You take the max of that. Instead of the sum, you take the max of that.
What was xi?
xi is one of the points in your data set. So here xi is one of the points in your data set, and so the cost is you take the distance of that point to the set of centers, you square it, and then you sum it up. That's the k-means cost. Okay, so the cost we will regard as an aggregate, and we will mostly focus on the sum. We won't focus so much on the maths. Okay. And Okay, so this is a query and cost perspective, and how do we expand, how do we use this language? And let's see an example, as we were saying, that for k-means clustering, this is the cost written in the traditional way, the distance of xi to c1, c2, ck whole square, the sum over this over all possible I. So what do we define as a strong coreset? Here is my definition of a strong coreset. But suppose D is the original data set, right? And Q is a proposed solution. Here, a proposed solution is a set of centers if we are a set of k centers if we are in the k-means setting, or it's a vector if we are in the regression setting. The Q is a proposed solution, and total cost FQ can be written as an aggregation over pointwise costs, often a sum. We'll focus on the sum, as I mentioned. So a coreset is a set of points xi wi, set of weighted points. Wi is the weight of the point xi, and the cost of the coreset, the cost of C on Q, written as FCQ, will be given as summation over I given I in C, I in the coreset, Wi times F xiq. Right? So think of Wi as basically multiple copies of xi at that same location. That's why it's Wi times fxiq. Okay, so the coreset cost of Q is given as the summation over all I belonging to the coreset Wi fxiq, and that's what we want to say. Okay. So as we mentioned, as I've already mentioned, that in the regression setting, let's say in the k-means setting, each point's contribution to the cost, written as small f xiq, is the square distance of xi to the nearest center in I. Right? In the case of the linear regression, right, where the total cost is aq minus b p norm of that, each point's contribution, each point i's contribution to the cost is, each point I is really a row of A, right? So AI dotted with Q minus PI, the P norm of that. I mean, again, it's a scalar, so just the P's, so that raised to the pth power, the absolute value raised to the pth power. So, and many optimization problems can be captured in this generic setting.
This W,
Yeah.
there's freedom in W, right? You choose your W.
We will choose our
Choose our W.
We'll choose our W. Yes.
But the data set inherently has a W of 1.
If the data set inherently has a W, then W will be incorporated in that W. No worries. Yeah. Because in choosing the point xi in the coreset, we will incorporate the W, and in giving a weight to that point, we will incorporate the data set's W.
Even if there is no weight, naturally they have a weight of 1, but
even if there is no weight, our points will be weighted. The coreset will be weighted. So here is the property that we want. What we want to get a coreset C such that for all possible queries, and this is very important to know, for all possible queries Q, we want FCQ to be within 1 plus epsilon of FQ and 1 minus epsilon of FQ. This is multiplicative guarantee that I was talking about. See, f of Q is the cost of Q on the full data. Right? What we are saying is that the cost of Q on the subset, on the coreset C, will be within a factor 1 minus epsilon and 1 plus epsilon of the cost of Q on the full data. Right? Does not matter what Q is. This has to hold for all possible Q. Right? That should strike a bell. Right? So that before the bell strikes, let us note down a few things. But epsilon will be a user-specified parameter. That as a user, you can specify the epsilon, and the size of the coreset will depend on that. And also this property will hold with probability 1 minus delta. That unless you're in the deterministic setting, we'll say that this property holds for all Qs together with probability 1 minus delta. That is, with probability delta, things can completely crash and burn, and an asteroid can hit the Earth. I don't really care. Okay, so why do we?
So the spectral classifiers could fit in this framework?
Yes.
With a query.
Yes. Spectral classifiers fit in this framework. And the queries are any vectors V transpose LV that we are calculating. That we are calculating. Okay, so why do we? So the question that you might ask is that aren't we just overselling things? Aren't we? Because why are we looking for this property for all possible queries? Why don't just let's say that let us look at this property only for the optimal query. Right, no, only for the optimal query that I say this property. And the problem is that you cannot really do that because you don't know the optimal query. And the optimal query that you find will depend on the coreset, right? So it turns out that if you don't know if I should go through the running pretty late. Okay. Maybe I'll just quickly go through this. It turns out, maybe I'll just say it in words. It turns out that if you assume the property that I said before, that you have this 1 minus epsilon and 1 plus epsilon for the full data, I mean for all queries, 1 minus epsilon and 1 plus epsilon of the full data for all possible queries, then what you can say is the following: that suppose Q tilde, right, is the solution that you have found by optimizing it for the coreset, right? Q tilde is that solution. Now, what you can guarantee, and Q star is the solution in the full data, right? That you have found using the full data, right? The query that minimizes the cost in the full data. Q tilde is the solution, that is the query that minimizes the cost in a coreset. And what you can guarantee is that f of Q tilde will be within 1 plus 3 epsilon. 3 is just a small constant. 1 plus 3 epsilon of f of Q star. Right? See, this is the cost of plugging in Q tilde on the full data. I have not written C out here. So the cost of the coreset solution, on the full data will be within 1 plus 3 epsilon of the cost of the optimal solution on the full data. Okay, so I have a 1 plus 3 epsilon approximation. And that's very nice because epsilon is something that we can tune. And it follows from the set of equations that we've written out here that I'm not going to explain. If you're interested, let me know. Okay, so the strong coreset gives us these properties, right? So then isn't this something that we've seen? Isn't this something like sketching? Isn't this something like property testing? Well, not quite. Right? Here are some differences. So in sketching, what we do is that, namely, that the transformation is data oblivious. Right? We apply something like a random projection. We apply like any other sketching matrix, and then that transformation is data oblivious. We don't keep the original data points. We rather keep linear combinations of it. Therefore, there's a loss in sparsity. Right? Even if the original data was sparse, the final sketch will not be sparse. However, the plus point is that it supports updating with insights and also for deletions, namely deletions. Deletions is a big open problem for us for linear sketching. Okay, in property testing, again, it's a slightly different setting because here you're allowed to see the full data, right? You're not allowed to use the full data in optimize. That's the restriction. In property testing, you're not even allowed to see the full data. You're allowed to only post some questions about the data that can be answered in sublinear time, sublinear number of questions, right? So therefore you cannot, I mean, this is not really the same thing. So how to create this? A first cut approach, right? Let's just imagine, I mean, let's just see some of these simple things that don't work before we go to some things that work. Right? So what if we do uniform sampling, and what happens for k-means and what happens for linear regression? Just quickly see this. So what about uniform sampling? So here is the one example, an obvious example for k-means that does not work for uniform sampling. Suppose we have n minus log n points in whatever cluster out here. We have log n points in another cluster out here that's very far off from this cluster. And this will not work for uniform sampling because if in uniform sampling you take less than n minus log n points, you won't touch this set. Right? Less than n by log n points. Less than n by log n points, you won't touch this set. If you sample with probability which is less than log n by n, you won't touch that set at all. Okay. So therefore, you'll be sampling only from points out here and there, and you'll be clustering things out here. Whereas the cost of this cluster is very large because it is so big, so it is so different from the from your original set of points. It's uniform sampling will. How about for regression? For linear regression, here's an example in uniform sampling that does not. But suppose your data set is something like this. It's a strange data set. I completely agree. And it's a made up data set. But that's what we do as theoreticians. What else do we have to do in life?
This is like exam answer steps.
Yeah, exactly. Suppose your data set looks as follows. That suppose the first D data points form an identity matrix, and all the other n minus D data points are all the same. 1000, 1000, 1000. Okay. So now, if you sample with probability with if you sample like only like n by d points or something like that, right? Again, you won't touch the first d points. You won't touch the first d points. If you sample less than n by d points uniformly at random, you won't touch the first d points. You will only sample from this data set. And because notice that because of the first d points, the cost of this regression problem is always zero. Right, whatever BPI, the cost of this, and if you don't touch this, the first d points, you will never get the cost down to zero. Okay, and the cost of this coreset solution will be not equal to zero, and therefore you will not have a multiplicative error. So, and your hopes are dashed. So, I don't have time to cover everything. Let me just mention this and quickly go to the important sampling part. So there are a few main approaches for constructing coresets. One of them is a geometric approximation. It's a geometric decomposition in which what we do we basically create grids. And sometimes these grids are a normal grid, and sometimes they're exponential grids. That is the kind of increase, and they kind of go in size exponentially. They are of radius r, then the radius 2r, then the radius 3r, 2 square r, etc., etc. Right, 2 to the power I times r, etc. Right? And they grow in that exponentially, and then we snap each of these points to these exponential grids, and that has proven a very effective technique in normal normal computation geometry. That is, in computation geometry for lower dimensions, right? Problem with this grid-based decomposition is that almost always they give you a coreset size which is exponential in d, which is fine if your d is less than 10. Right? But today's dimensions are not less than 10. Okay. So, so the geometric decompositions, they're okay, but they typically give an exponential in dimension kind of dependence. The stronger, the quote unquote stronger method, and people would dispute me here, are the important sampling based methods in which we define a particular sampling score known as sensitivity. What we won't cover here is that there's a new set of coreset algorithms that use gradient descent and its variants, namely Frank-Wolf algorithms, right? In order to choose some of these data points, and I won't go in there. We'll be happy to talk about it. So, geometric decomposition. Let us keep this. Okay, let's go to important sampling. Important sampling, we say that Pi is the probability of sampling the ith point, and each sample, right, we scale appropriately to keep the cost function unbiased. For instance, if the cost function is ai transpose q to the power p, right, then if the pth point is sampled, then you have to scale it with 1 by pi to the power 1 by p. Right? Because if sampled, it will be raised to the power p. Right, and so that pi and I want that pi and this and the pi of the probability of sampling to be cancelling out. So I have to do 1 by pi to the power p. Whatever, you can work out the right way of sort of unbiasing it. That's an easy exercise. The big question is the following: how do we design the sampling probabilities? Right, and there was a very nice set of work sort of path-breaking work on this by Langberg Schulman in 2010, followed by Braverman, Feldman, Lang, Lang, Langberg. I think it should be Langberg, Statman, and so in 2016. That sort of said that here is a very interesting way of defining the sampling properties. That suppose I define this code SI. Right? SI is defined as the sensitivity of the point I. So how do I define sensitivity? That you take all the points you take a particular query Q. For that query Q, you calculate the total cost. That is nothing but f of xjq, right? The contribution of the point j to the solution proposed by Q. Summation f of xjq, and then you see what is the contribution of the point I to this total contribution. So that fractional contribution is the sensitivity of the point I. Right? It's like saying that in a quiz team, right? So in a quiz team, you have experts in various fields, right? You have somebody expert in cricket, somebody expert in politics, etc. Now, depending you're asked different questions. Now, if the question is of cricket, then the fractional contribution of the cricket expert is pretty high because he or she is able to answer all the cricket questions correctly. Right? If the contribution is about politics and the fractional contribution of the politics person is pretty high. But if somebody is there who knows a little bit of everything, but nothing in specifically, then their fractional contribution is low for all the possible queries. Right? Because they sort of know a little bit of everything. So there is no particular query in which they are really excelling. So that is what is defined as the sensitivity. Right, of a particular point I. So what Langberg et al. Say is that now calculate the sensitivities. Notice that these sensitivities are between 0 and 1 because the numerator is a part of the denominator. Okay, so therefore these are always in 0, 1. And now sample points according to this sensitivity. Okay, and sample points according to the sensitivities, and that will be good. Also, one important point is notice that this is the worst case sensitivity for any point. So for any point I, we look at the worst possible Q, right? That sort of boosts its sensitivity to the highest, right? So the sensitivities of different points can be made worse by different queries. For instance, the cricket expert answers a cricket question, a politics expert answers a politics question. So both of the sensitivities are pretty high. Okay, the worst case can be different for every point. However, that's okay. They all are between 0 and 1, and we can sample according to them. Okay. So why does this work? Again, I won't go into the proofs, etc. Just in English. That under any set of probabilities and a fixed query Q, we consider suppose we consider the variance of this FCQ, because FCQ is a random variable under the sampling that is happening, and we consider the variance of FCQ, and it turns out that choosing PI proportional to FXIQ minimizes this variance. Right? You can show that fairly easily, and choosing PI to be bigger than or equal to sensitivity I bounds the variance for any particular fixed query Q. Right? Because of bounding the variance, it bounds overall spread of this particular random variable. But there's a big but. Right? The gorilla is scratching its head. You needed a guarantee for all queries. You promised me a guarantee for all queries. How do I do that? There are infinite number of queries, right? Because we're doing what you just mentioned, right? I could give you a guarantee for a single query with some probability, right? How do I generalize to an infinite number of queries? Because I cannot do the union bound. Right, because the union bound cannot take a union bound over infinite set. It turns out that you have to use some tools from learning theory in order to do this. And namely, these tools are related to VC dimensions and things like that. Basically, that if you can cover the entire query space by a bunch of balls, by something called an epsilon net, you can take a union bound over that epsilon net, over that finite set epsilon net, and that will be enough. I won't go into any more details related to this. Feel free to ask me questions. And basically, the proofs here are exactly the same as the proofs that you would do in learning theory, and the same kind of tools. And therefore, the total number of samples finally becomes the following. This is important to note, that the total number of samples that you need to take becomes proportional to what is known as the dimensionality of the query set. And this dimensionality comes with basically is a representation of how complex the query set is. Right? So the complexity of the query set, and this is typically the VC dimension of the query set, times the total sum of sensitivities, and this is related to how kind of complex the data structure is, times epsilon square times log 1 by delta, and these are standard terms. Right? These are the two kind of error parameters that we have. Okay. How to estimate the sensitivity? Man, I didn't even get to that planning. We'll finish on time. How to estimate the sensitivity? And that's an important concern. Huh? Estimating sensitivity is almost as hard as solving the problem. That is true. Luckily, there are other ways out. So it's often possible to take the structure of the problem and to define and to be able to define upper bounds on the sensitivities. And it turns out that any of these upper bounds will work. Right? The devil is in deriving non-trivial upper bounds to the sensitivities for each problem. That's why we have this so many papers in this area. Otherwise, there would be just one paper, and it would be terrible for all of our research agenda. Okay. So let us not go into this bounding sensitivity upper bound for k-means.
If it's just one paper, people always finish at 9.
Yeah. Okay, so properties of coresets. So coresets have nice additive properties. That is, you can take union of coresets and that will still be a epsilon coreset. You can take coresets of coresets, and that is composable. And we won't go into. Let me just quickly mention this because this is important. It turns out that the existence of a coreset guarantees a streaming algorithm with low space. Right? That's a very interesting property. So how does it do that? Basically, here is the idea, which is a wrong idea here, and I'll correct this. And here is an idea that suppose you have a stream passing through it. So what you do is that you break it down into small chunks. You take the coreset of each chunk, right, and you combine it with the coreset of the next chunk, and you combine it with the coreset of the next chunk, and you only maintain these coresets, right, as the chunks flow by, right, and finally you have only the small coreset of the entire stream, and that would be enough to calculate anything. To calculate whatever property you wanted to calculate, because coresets are problem specific. Okay, so take a property that you wanted to calculate and keep on calculating its coreset in these small chunks, and that would be enough. However, this picture is completely wrong, because if you think a little bit about it, the coreset guarantees are not being composed in a very nice way. Because see, this coreset has a property that there is a 1 plus epsilon coreset of this and this. This has a property that it's a 1 plus epsilon coreset of this and that. Therefore, of these three, it's a 1 plus epsilon square coreset. 1 plus epsilon whole square coreset. This is a 1 plus epsilon whole cubed coreset. Right? So therefore, if I go L levels down, it will be a 1 plus epsilon to the power L kind of coreset, which is a terrible thing, because it's growing exponentially in the number of levels. So this is not the right way of composing it. Any question? The right way of composing it is something which is a little bit clever, and I won't show you the code for this. I'll rather show you the picture. It's called margin reduce. It's basically like keeping a binary counter. That you have imagine you have these empty boxes, and then the first chunk comes, you prepare a coreset for that, you keep it in the first chunk. The second chunk comes, you move the coreset of the first chunk to the second box, and then you place the coreset of the second chunk in this first box, empty first box. The third chunk comes, the first two are empty, and the first two are full. What do I do with the coreset of the third chunk? What you do now is that now you create the coreset of these two chunks and keep it in the third box. And then you place the coreset of the of this fourth chunk in this first box. So notice what is happening is that it's really like a binary counter that is happening, because we have like one, we have this 1, and then we have 1 0, then we have 1 1, then we have 1 0 0. Right? So basically, you kind of imitate this binary counter as it goes down, and it turns out that this is a very effective way of combining coresets, which has these properties. That if your original coreset algorithm gives you order S-sized coreset, then this merge and reduce streaming algorithm that I showed you has working space only S log n, right? Has coreset size order S and returns the epsilon log n coreset. So the guarantees become a little worse, right? Because now there are log n levels, right? Because of this counter thing. Because each bit can be incremented at most log n times. Therefore, it's the epsilon log n coreset, and therefore you need to reduce the original epsilon by 1 by log n factor, which is not a big deal.
So this is equivalent to just working with the proper binary tree as opposed to the skew tree or something. Right?
Yes.
And you're maintaining things in the stream.
You maintain. Absolutely. Yeah. So you call this technique with epsilon value epsilon. Okay. So why do I mention this? We'll mention this because we'll kind of need this in one of our main algorithms. Okay, so here's one small result, finally. One small result that we had. Here's a question. A question that we asked is that does regularization of the problem have an impact on the coreset size? Right? And there's been existing work that shows that yes, it does. Because in some sense, what regularization is doing, it's kind of reducing your dependence on the data. Right? Because you are kind of adding a prior to your optimization function, and therefore you're reducing your dependence on the data. For instance, this is known as the ridge regression regularizer, famous ridge regression. Okay, and you're adding this lambda x2 square, right? And it turns out that for this, the coreset based on orthogonal basis of a over a and then a lambda matrix have or equivalently the sensitivity is enough, right? Does this have a smaller coreset size? Yes, it does have a smaller coreset size. I have not written this. Yeah, it does have. I don't know. Something happened. It does have a smaller coreset size because for regular regression, a coreset size of the order of rank of A is important. For this particular problem, a coreset size which is like this is enough. And notice that this ratio is less than equal to the rank of A because the sum goes over all possible eigenvalues, and this quantity is less than equal to 1 for each of the eigenvalues. So therefore, this quantity is less than equal to the rank of A, right? And it can be substantially less if you increase your lambda. So we know that for ridge regression, we can get a coreset which is less than equal to the coreset for regular regression. What about other regression problems? What about lasso regression, for instance, which is so ridge regression is x2 norm square. Lasso regression is x L1 norm, right? But you can say that I have the same idea, right? I'm just sort of introducing another prior. Right? Rather than use the same prior, rather than use the Gaussian prior, which is used in lasso, I'm just introducing another prior, but the same effect should hold. Turns out that it does not. Very interesting, right? It turns out that you can show that a combination of P norm and a Q norm on the X has a smaller size coreset only if P equal to Q. Right? That is, if P not equal to Q, what you can show is that you can give an example, you can construct an example where the coreset size will be of the same size as the coreset size for this problem. Okay. So regularization does not always reduce the coreset size. It can reduce the coreset size. There is the main result. The tensor factorization. So we tried to see the effect of coresets on tensor factorization. What is a tensor? Tensor is a multidimensional array. right? This is an example of a third order tensor, for instance. Right? Used in many settings, for instance, signal processing, neural network training, etc., etc. Right? So, what do I mean by tensor decomposition? Well, first we need to define the notion of a rank one tensor. A rank one tensor is nothing but the outer product of three vectors, A, B, C. So every coordinate of that tensor is A, I, B, I, C, I, A, I, B, J, C, T. That's the IJK coordinate of that tensor. So rank K decomposition of a tensor is akin to writing a given tensor as a sum of rank one tensors. That's just like in a matrix. Just like a rank decomposition of a matrix is about writing a matrix as a sum of k rank one matrices. Similarly, we want to write this as a sum of k rank one tensors. Why do we want to do this? Or why not? Because rank K decomposition of tensors have very nice properties. First of all, there is a lot in topic modeling. Because unlike matrices, there's a very cute result by Kruskal. It's the same as the graph theory Kruskal. That says that unlike that for tensors of rank for tensors of order 3 and more, the rank decomposition of a tensor is unique. Notice the rank decomposition of a matrix is not unique. Because UV transpose, I can insert a matrix inside, which is PP transpose, and the product will still remain the same. But for tensors, you cannot do that. Right? So the rank decomposition of a tensor is unique, and that's very useful in these algorithms. Okay, and so ranked tensors are used in training neural networks. So optimizing certain two-layer neural networks can be calculated as can be written as calculating tensor factorizations. They are also used in topic modeling. So they are very useful, practically useful. Okay, so how are they useful in topic modeling? A very high-level idea. Again, just using pictures. What is topic modeling? The topic is basically this: that suppose you have a collection of documents. So every document is represented as a bag of words, right? Just as a set or a multi-set of words. Okay, and every document, I can imagine, has been generated from a topic distribution, right? That every topic, what is every topic? Every topic is nothing but a probability distribution over words. And now you just imagine that every document corresponds to a fixed weighted probability distribution over words, right? And we'll basically pick the words according to that particular probability distribution, and therefore that's how every document is generated. Right? And how to learn this topic? How will I be able to find out that which document corresponds to what probability distribution, what set of topics? And the standard method is by using the moment method. It's basically the following: that if you are using only matrices, okay, time. 5 more minutes. That's it. You can just take a covariance matrix and take its spectral decomposition, and that's enough. Right. Similarly, what you can do is that if you want to go a little bit further, what you can do is that you can take the three order tensor of the words and factorize that, and that probably gives you underlying topics of this document distributions. Okay, so here is what we asked, and I'll tell you what we got, and we'll kind of wrap up there. That what we asked is the following: that creating the three-order tensor from a stream of documents needs spaces potentially ordered d cube, and it takes a lot of time, n d cube, right? Because there are n documents, and then you have a space of d cube which you need to fill. So it takes n d cube time. So what we asked is the following: that we are calculating AI tensor with AI, where AI is every document. What we want to do is that we want to sample each of these documents, right? Sample some of the documents and create the same tensor out of only the sample, right? So the space required might be the same. Right, but because we're creating the tensor using only the sample, right, the time required will be much smaller, and we want to guarantee that using the sample tensor gives me similar factors. Right? Can we do this? So there are three questions, right? How many points do we need to sample? Number one, question number one. Question number two, what is the working space that we need? Question number three, what is the update time that we need? Okay. In order to kind of keep on updating this. So as I mentioned that offline algorithms can be converted to streaming by merge and reduce. But then what is the optimal if we compare with the above trade-offs? Okay. So we won't go into the details of this. There's no time. I'll just show you the results. Okay, So on top are the existing algorithms compared in terms of the sample size, the update time, and the working space. Okay, what you see are algorithms from 2009. We had an algorithm in 2009, and there are other algorithms. So all of these algorithms are in the offline setting, but they can be converted to a streaming setting. Right? What we are proposing are purely online algorithms, right? And if you look at some of them, they take substantially less space and substantially less update time. Update time is d square amortized, which is much less compared to most of them, except for the streaming apps. Right? And the space is like d to the power p by 2, which is much less than the streaming apps. So we are kind of winning in most of the aspects in terms of if you compare all three of these. So as I promised, we'll wrap it up quickly. So these corsets have a lot of other applications that we have been talking about, and one of the applications that we have been working in is in compressing neural networks, right? Where we consider the neurons as the points and the data as the queries, right? And it turns out that you can do that. We've also been working in Coresets. There's a related set of completely applied techniques known as data set distillation. And the idea there is the following: that suppose we have the MNIST data set, right, which is a very famous data set. 50,000 images that are categorized into 10 classes or something. What it says is that look, I don't need to take all these 50,000 images. I can only take 100 images out of this 50,000, create this 100 images empirically, right? And by training on this 100 images, you will get a similar result as you do by training on the 50,000 images, right? Empirically, all of this is completely empirical. Can I think about this in the Coreset setup, right? Similarly, people can do this for this 110 digits data set. Can I think about this in the Coreset setup? It turns out that you can, right? You can. There's a very interesting set of results in which you can imagine you can think about every neural network as what is known as a Gaussian process, right? Which is basically a collection of Gaussians. And by looking at that, you can start creating the coresets that will preserve this Gaussian process, that will basically maintain this Gaussian process, and you get good performance, and you get some empirical, some theoretical results also. So this is our performance as a book. Right. Even this wants me to finish. Promise you, won't take 2 minutes. Okay. So you get good empirical performance as well as you get some theory behind it.
You're modeling the data in the Gaussian process or the neural network?
No, the neural network is the Gaussian process. Neural network. Okay. So privacy and security. So Coresets are very interesting applications in privacy, which I admit that I've just started looking into this. We have not really fully explored this. That basically Feldman and all show the existence of private Coresets. Remember that Coresets have the property that for all queries, it was giving me a cost which was close to the original cost. Now, if you can on top of that ensure differential privacy for the Coreset, then what you are guaranteed is that you're getting a differentially private sort of subset that approximates the cost for an infinite number of queries, right? Which is not a trivial thing to get, because the more queries you ask, the more information that you leak intuitively. So thereby, Therefore, getting private subsets, which work for a lot of different queries is not very easy. But if you can get private coresets, you'll be able to solve that problem. And Feldman shows the existence of private coresets, right? For a lot of different problems, but he does not really give algorithms to construct. Non-constructive. We're looking into some algorithms, and we have some potential algorithms for regression problems. We'll see. Coresets have also been applied to fully homomorphic and
Why is this even possible? Why can't you have a cluster of points and one point that is close to infinity, and then you have to have that point in the coreset?
So this is possible only in an additive setting, right? Not in the same kind of guarantees.
I think it also matters what the query point is, right? So one guy is really far
Yeah.
away.
Yeah.
That's for all queries.
No, but in that type queries, then he already knows himself, right?
No, it does hold for all queries, but it holds with an additive guarantee. So maybe if one point is very far away, you can leave out that point and still be okay with it.
So it's infinitely far away. The additive guarantee is also.
That is true.
You mean the data is such that the function that you want to differentially privately learn is leaking information about a certain data point? I think that is anomaly. I mean, differential privacy will only say that you will only learn what you could from the output of whatever, I don't know, optimal clustering or something. So if there is it's like if we are doing something about salary of people and some super high person is there, that you will,
That you cannot help. Yeah. Okay. Just to wrap up. So coresets are a successful application of randomized algorithms in machine learning. It has spanned multiple communities: computational geometry, machine learning algorithms, and there are a few repeated things that come up: important sampling, building on rough approximations, clever use of low dimensional projections. The reason I find it interesting is that it's a combination of theoretically non-trivial questions with practical applications, right? And a number of recent papers show empirical validations of this. One slight problem with this whole theme is that the questions are still largely focused in the unsupervised setup and on worst case data assumption. That is, we don't assume anything about the data, right? So what can we do if we take a Bayesian view, for instance, of the data? Those things have still not really been explored. Some other questions are, can we come up with better than worst case errors, data dependent errors? Can we have more applications in supervised settings? We have some results that I'll mention if anybody is interested. And one-on-one, can we have coresets in dynamic settings, in data deletions, more importantly? Neural inclusion is easy, data deletion is hard. More deterministic constructions. What are some connections with dataset distillation? Can we formalize that? And more practical implementations is something that is really needed for somebody to do. Okay, so here are a few references, and I'll be happy to take questions. So, get over, let me a little bit.
So with k-means in Rn, what is the size of a coreset for a fixed epsilon?
I believe it's some power of k. I don't remember exactly. Some k square. Doesn't depend on n at all. K and epsilon. Epsilon is the error for the coreset.
So I was trying to constantly keep the parallel of graph classification. So there also, the thing is, we do sort of do random sampling of edges to build a classifier, but it is random sampling after we realize which edge is important, etc.
No, here also, right? We're calculating the sensitivities.
Yeah, I agree. So I was just wondering, does the sensitivity play a...
Yeah, totally.
Is there a graph theoretic analog of what the sensitivity captures?
But here it's not sampling, right? Because you can construct points that were not in the original data.
No, in what I showed it's sampling.
Not in the example that was there.
In what I showed it was sampling only, right? In the dataset distillation, the results in which you empirically construct examples are really empirical. There's no theory behind that. Most of them, right? Theory is mostly behind the subset choices. Where the data set is a subset, the chosen data set is a subset of that. And yes, coming back to your question.
And
So-
here also the thing is there is an underlying set of queries queue that you work with, where
Right.
the sensitivity, etc. is defined.
Yeah.
Also, what is the set of queries when we are talking about the standard graph classification?
So the standard graph classification, the set of queries is very easy because what we want to preserve are the sort of the cut vectors and the cuts, right? Or in more specific terms, things like V transpose LV,
Yeah.
where it is the Laplacian and V is any matrix.
Oh, so we just
So
work
V is the
with
query.
net on that.
Yes, we work with the epsilon net on that space on this V. And in fact, the sensitivities that you take in the graph classification are exactly the sensitivities that I mentioned that work for the regression, which is basically that you calculate the eigenvalues of the eigenvectors of the Laplacian and take the row norms of the eigenvectors, and that exactly works as the sensitivity, right? So, it turns out that it also works in the reverse way, because what we have recently done, and I didn't get to mention it here, is that so the BSS result, the Batson, Spielman, Srivastava, is basically graph classification in a deterministic setting. Right? But that effectively works only in the L2. That implicitly is in the Euclidean space because it works with V transpose LV, and it's about preserving eigenvectors, etc. In the Euclidean setting. Now, can you take that work and try to build this kind of pacifiers in the LP setup, right? Where you're preserving LV raised to the power P, LV P norm to the power P norm. It turns out that yes, right? You can take the same notion of barrier functions. They work with the notion of barrier functions, etc. And you can take the same notion and you can generalize it a little bit to work in the LP norm, and you get a deterministic coreset for LP regression and other things. So that loop we have recently been able to complete, and we'll submit it somewhere. We don't know.
More
Questions?
questions.
Thank you.